reference to. Okay. Okay. So under manufacturing processes, we have studied different type of manufacturing processes. Okay. So these manufacturing processes are first, you might, if you remember correctly, the first manufacturing process, that is welding, casting. Then we have another manufacturing process, welding. Then we have machining processes, or which is also called as material removal processes. Then we have mechanical working processes, or which are also called as metal forming processes. So it is important to note that this your course metal forming processes is one of sub branch of your manufacturing processes, which is also called mechanical working or metal forming processes. Then in manufacturing processes, we might have studies powder metallurgy and plastic technology. So from this, we can understand that we are going to understand one type of manufacturing processes, which is metal working process, which is known as metal working processes or metal forming processes. Okay, so some introductory part you might have studied during your second year, but I will recap it. Okay. So under mechanical working or metal forming processes, what we actually do in mechanical working processes, the raw material is converted to a given shape and size by the application of external forces. The metal is subjected to stress. Therefore, it is a process of changing the shape and size of material under the influence of external forces. Okay. So what we are going to do in metal forming processes, we are applying certain external force on a metal block, and it is converted into a desired shape and size. Okay. So this is introductory part. If you see metal forming processes, metal forming process is the largest group of manufacturing processes in which lasting deformation is used to change the shape of metal workpiece. Okay, how this shape is changed? The shape is changed under the action of external forces. Okay, under the action of external forces, how we apply these external forces? These external forces are applied through a tool, and the workpiece is generally kept above or inside the die. Okay, and these forces, how much we need to apply? We have to apply that much force that the stresses induced in the workpiece or the metal workpiece exceeds the yield strength of the metal. Okay, you might not be able to recall what is yield strength, but we will we will discuss what is yield strength in this lecture. Okay, and what happens? The metal takes a shape which is determined by the geometry of the die. Okay, there may be some impression also on the tool, but the tool, this your workpiece is kept in between your tool and die. Okay, so this is how we are trying to understand metal forming processes. Okay, so now we will move to the classification of these metal forming processes. How these metal forming processes are classified. Okay, so there are two major groups in metal forming processes. One is bulk metal forming, and another one is sheet metal working. Okay, so from the bulk forming processes, in the bulk forming processes, what we do, generally the big input material or size of input material is large. Okay, but in the second type of metal working processes, which is called sheet working processes. The material is in the raw material is in the form of sheets. Okay. So in bulk metal forming processes, the input material may be in the form of billets, rod, or slab. Billet, I will just give you an overview of what is the size of billet. The billets have cross-sectional area approximately 36 inch square. Okay, or if we take in centimeter, then it is approximately 230 centimeter square. Okay, so in chat I am seeing questions. It is good if you are asking questions, because it will be I'm speaking from one side and I cannot hear you. Okay, so in bulk forming processes, it is written at stock has I V upon A. So V upon A is nothing. It is volume upon area. Okay, so volumetric ratio is high in the case of bulk metal forming processes, while in the this is for volume, this is for surface area. Okay, so in the case of bulk metal forming processes, the volume is converted into the volume remains constant, but the surface area is increased. Okay, while so okay, sorry, this we are talking about stock. Okay, so stock has high volume upon area. Okay, so if we see the ratio of volume upon area in the case of bulk metal forming, it is very high, while in the case of sheet metal forming processes, because the area is very large, we can understand if we see a sheet, the area is very large and volume is very low. Okay. So in the case of sheet metal working processes, the volume upon area ratio is low. Okay. If we okay, so there this is how this bulk metal and sheet metal working processes are classified. So under bulk forming processes, there are a number of processes: rolling, forging, extrusion, then wire and bar drawing. We will discuss about these processes in the today's lecture. Okay, and under sheet metal working processes, we have bending, leaf drawing, and cutting. Okay, so okay. So now we will try to understand bulk forming processes. In bulk forming processes, we already know that volume to surface area ratio is very high. So bulk refers to the part with relatively low surface area to volume ratio. Okay, this is written in reverse order. The area upon volume ratio is low, while similarly volume upon surface area is surface area ratio will be high. Okay, the starting workpiece shapes may be cylindrical billets or rectangular bars. Okay, so as under bulk forming processes, we will discuss. I will just give an overview of these processes. Then, because we are going to discuss these processes in detail in further chapters. Okay, further lectures. Okay, so one of the metal forming bulk metal forming processes is rolling. Under rolling, the workpiece is it's rolled in between two rolls, and the forces are applied on the surface of workpiece, and its dimensions are reduced to a desired shape. Okay, this is rolling. Why it is called rolling? Because the material is getting deformed under the action of two rolls or more than two rolls, depending on the requirement and say inside of the work finished product. Okay. Another we have another type forging. In the forging, what we do, we have tool, or sometimes it is also called as die. Die, it is written die, but you may consider upper part as tool and second lower part as die. So under forging, what we do, the forces are applied over the workpiece, and the workpiece is kept in between the die and tool. Okay. So as soon as we apply the forces on tool, this workpiece is deformed in the desired shape, which depending upon the shape and size of tool and die. Okay. And we have another type of bulk metal forming process. I'm just giving an overview of these processes. Okay, we will discuss in detail in coming lectures, because we are going to extend these processes in later part of your this course. Okay, so another type of bulk metal forming processes is extrusion process. Under extrusion process, what we do, this is our initial workpiece, and it is forced to pass through a die. This is your die. So this is just a block diagram. We will discuss in detail that what is the shape of die, what are the different nomenclature or different geometry design which are considered in die design. Okay, so what is done in extrusion processes? This workpiece is pushed through a die. In this, you can see the force is being applied from the left hand side. Okay, so since the force is being applied, this workpiece will move towards right. Okay, since this workpiece will move towards side, there is a narrow die opening. Okay, and the workpiece is passed through this narrow die opening and converted into new desired dimensions. Okay, so this is how the metal flow takes place in the case of extrusion processes. Okay, so then we have you can see by seeing extrusion and wire drawing and bar drawing, you will see both figures looks like same, but there is a major difference. In extrusion processes, what we are doing, we are pushing our workpiece through the die. Okay, we are pushing. Okay, we are not pulling. We are pushing this workpiece material inside a die, and material is converted into the desired shape. And while in the case of wire and bar drawing, what we are doing, this is our workpiece, and this workpiece is being pulled. Okay, there is no push. You can see the force is applied on the right hand side, so workpiece is being pulled through a die. Okay, so this is how this wire or bar drawing works. Okay, so we will discuss in detail later. Another, we have seed forming processes. In seed forming processes, forming and related operations performed on metal sheets, strips, or coil. Okay, this I have already discussed earlier, that high surface area to volume ratio. Okay, or low volume to surface area ratio. Okay, you can say vice versa also, high surface area to volume ratio or low volume to surface area ratio of starting metal. Okay. Uh, Often this work is done on presses, and therefore it is called press working. And because presses are used to perform these operations. Okay, so some parts are called stamping, tooling that are used. These are called punch and die, as I discussed earlier. Okay, then since we are going to discuss about metal forming processes in detail, so the first important topic that we must understand how our material is going to behave under the action of forces in metal forming processes. Okay, so I will give you some examples like suppose we have to produce a aircraft uh, aircraft or automobile structure from the piece of a metal by stretching it. Okay, so what we are stretching a metal piece to convert it into the shape of some part of aircraft or automobile structure. So it is being stressed. So we can understand what kind of stresses will be developed in the workpiece. So the stresses which will be developed in the uh, uh, in the in the workpiece, that will be tensile in nature or tension type stresses. Okay. Okay, let us take another example. Suppose we are supposed to forge a gear. Okay, through forging processes, we are forging gear disc from a cylindrical piece of metal. So what we have to do? We will put. Let me come to the forging. Okay, suppose we are producing some gear disc using this forging processes. So what will be the shape of die and punch? It will be replica for die and it will be replica of your gear disc. And since we have to produce gear disc, we will produce a cylindrical or a square piece inside your in between your tool and die, and the force will be applied on the tool and die, and this your workpiece will be converted into the shape of gear disc. Okay, so since we are applying forces, so what kind of stresses will be developed in this metal workpiece? Obviously, these stresses will be compressive in nature, or compression type uh, stresses will be developed during the manufacturing of gear disc. Okay, so we were on material behavior. Similarly, uh, during sheet metal processes, there 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 may be requirement of making holes. Okay, suppose we have a sheet. Okay, and we have to create holes or cut holes on the surface of sheet. Then what will be required? What will be required? The punch will move over the sheet surface, and the shearing stresses will be developed, and the required hole will be produced. Okay, so this is how the material behave in different loading conditions. Okay, so there are a number of properties that will be important. Uh, the common type of loading which we apply during during the metal forming processes, these are compression, tension or tensile, shear, torsion, or combination of all these four. Okay, so the common type of loading are compression loading, or the common type of stresses that are developed during metal forming processes in the material, that are compressive, tensile, shear, and torsion, or combination of these four stresses. Okay, so how? Okay, so now we will try to understand where and when these stresses are developed. So, as I shown you earlier, rolling, forging, and extrusion. Under these three processes, rolling, forging, and extrusion, the compressive stresses are developed. Okay, how we can understand this? So we will come to the rolling. Okay, This is rolling. In rolling, what is being done? This workpiece is being rolled in between two rolls or more than two rolls. So you can see this portion is under the action of compressive stresses. Okay. So what kind of stresses are developed during rolling? Compressive type of stresses are developed during rolling process. Similarly, in the case of forging, the workpiece is kept in between the die and tool. So the force is applied from the upper side. So this what kind of stresses are developed during forging? Again, compressive type of stresses are developed during forging. Okay. Similarly, in the case of uh, extrusion, uh, since we are pushing this material from the left hand side, this force is F is applied. So since we are forcing this metal block to pass through a die, so what is being done? This metal workpiece comes under the action of what kind of stresses are developed. That is, these stresses are compressive type of stresses. Okay, and the material is coming out of this die opening. Okay, so this is how in we can understand that under rolling, under forging, and under extrusion, compressive type of stresses are developed. Okay, so now we will this compressive type, where compressive type of stresses are being developed. Examples are rolling, forging, and extrusion. Now we have another under stretching. As I took example of automobile structure, what we are doing, we are producing some automobile part or or aircraft structure by stretching a metal block. Okay, so while stretching, what kind of how the force will be applied? Force will be in nature, the metal block will be pulled from both sides. Okay, so this way metal block will be stretched, and the kind of stresses that will be developed during tensile will be tensile stresses. Okay, so from here also you can see under okay, I am not taking diagram of any stretching. Okay, no issue. So we can easily imagine how this metal block will be stretched and converted into some uh, some aircraft structure or automobile structure by applying tensile forces. So the kind of stresses that will be developed will be tensile stresses. Okay. Similarly, we will come. Uh, there are some processes where both kind of stresses are developed, like in bending. Okay, in bending of sheet metals, the compressive stresses are developed uh, uh, in the one side, and while the tensile stresses are developed on the another side. Okay, so one side will be in compressive under the action of compressive stresses, and another side will be under the action of tensile stresses. Okay, now sorry, this is not bending, this is cutting. Okay, it is a typo error, it is cutting. Okay, so here stresses is let me put, let me highlight it, note it is cutting. There is no chance of error. Okay, so it is not. Here stresses are developed under uh, cutting or uh, punching. Punching means uh, creating holes inside on a seat surface. Okay, so what happens in the case of punching? The the shear stresses are developed, and these shear stresses are uh, enough. Uh, these shear stresses are much enough to cut the hole on your seed surface. Okay, so this is how we are trying to understand what kind of stresses are developed when the material is loaded by uh, tensile force, compressive force, shear force, or torsional force, or a combination of these processes. Okay, there are a number of properties that we must to understand the behavior of uh, materials under in the metal forming processes. These properties are strength, hardness, toughness, plasticity, and malleability. So we will discuss about these properties. Okay. Okay. So you might be aware of how sorry how we are going to study these properties. We have one test which is normally known as tensile test. Okay, so under tensile testing, what we can do, uh, we we draw stress strain diagram, and we are through this stress strain diagram we are able to find modulus of elasticity, elastic limit, elongation, proportional limit, reduction in area, tensile strength of metal, yield point, or yield strength. Okay. Okay. Okay, so under tensile testing, what we do, the stress is calculated from the load and the strain, and uh, these are plotted on strain curve. Okay, so if these plots can be of two types. One is called nominal or engineering strain, and another is true stress and strain. Okay, so first we will try to understand nominal or engineering stress strain. Okay, in nominal stress strain, what we do, it is also called as engineering stress in tensile test, is defined as the ratio of applied force or applied load F to the original cross-sectional area of the workpiece. Okay, so this is how nominal engineering stresses are calculated or computed. Sigma n equal to F. F is your applied force, and AO is your original cross-sectional area. Okay. Okay. And how the nominal strain is calculated? It is defined as change in length upon original length. So LO is your final length. L is your final length, or LO is original length, and it is divided by, this difference is divided by original length. So change in length may be called as delta L upon L. Change in length will be delta L, and when it is divided by LO, this gives you the nominal strain or engineering strain. Okay. So using these nominal stresses and strain, what we do, we can draw the stress strain diagram of the test specimen. Okay, so suppose I'm showing one stress strain diagram which is computed for mild steel. Okay, so you might have studied this stress strain diagram already in your manufacturing process course or other courses also, but we will for the recap or reminding, we will discuss what are the different points on this stress and curve. So here you can see this is our origin, and there is a line from O to A. Okay, so this, and what is this O to A line? this A is representing your elastic limit. Okay, what is this elastic limit? This elastic A is your elastic limit. It means the Hooke's law, that strain stress is directly proportional to the strain, is perfectly satisfied up to point A. Okay, this Hooke's law, that is stress is directly proportional to strain, is perfectly applicable up to point A. Okay, but if we apply more forces beyond point A, that is, if we continue loading the workpiece, what will happen? There, the stresses are not directly proportional to strain, but the strain value is slightly higher. Okay, the strain is the strain value, that is this strain value is slightly higher than the strain. Okay, so this is beyond point A. It is not a line. It's slightly coming towards strain. Okay, okay. So this point A is your proportionality limit. But what is the one more property of point P? This strain is slightly higher, but the material is able to regain its original position, okay, after the removal of force. It is important to note that as soon as we release force, this material is able to regain its original shape, okay, original shape and size. But beyond point A, the strain are slightly higher, okay. But as we move further, we find another point Y, which is also called as proof stress. Okay. Okay. In this point is basically calculated by the this point, that is, it is also called as yield point, is usually determined as the point on stress strain curve that is offset by 0.002 of elongation. 0.002. Then this is your elongation. Okay, so this point is calculated based on the 0.002 elongation, or 0.2% of elongation if we are talking in percentage. Okay, this is how this your yield point is decided. Okay, so if we continue uh, uh, apply forces on your workpiece, beyond this, what will happen? Your material will be deformed uh, with more strain, but a permanent deformation will occur on the on your workpiece, okay, on your test specimen. Okay, so beyond point Y, what will happen? There will be some permanent deformation on your test specimen. If you so after point Y, if you even release your applied force, the specimen will not be able to regain its original shape and size. So there will be some kind of permanent deformation after this point Y. So under this region, up to point F, we will discuss what is M, what is F. But under this region, there will be some permanent set of deformation on the test specimen or your workpiece. So this is your dividing line. The left hand side is your elastic region, and the right hand side is your plastic region. Okay. So beyond Y, it is your plastic region, and before Y, it is your elastic region. Okay, under plastic region, what happens? We have another important point, that is point M. In some books, you may find it is written as U, but I have written it as M. Somewhere you may find it for name as U. Okay, so this is the point. If we continue loading on the test specimen, there is a stress value, after which if the material continued deforming plastically, and the material is fractured at certain point. This is called your F point, that is the fracture point. So in this stress strain diagram, we can see that for failure or fracture of material, there is a maximum force or maximum stress that can be induced inside your test specimen, that is equal to M. If we apply stresses more than this value, the material will be fractured, or material will break into two pieces. Okay, so for it is important to understand that this U or M point is very important for us in while we are dealing with metal forming processes, because this is the point where your plastic deformation is starting, and this is the point beyond which the material is getting filled. Okay, so for for, for metal forming processes, which region we have to choose for deforming metal workpiece? We have to choose the region between Y and M. Okay, between the yield point and ultimate tensile strength. Okay, this point is called ultimate tensile strength. Okay, it is the point. Okay, uh, at which plastic deformation becomes unstable and neck forms in the specimen. Okay, so this UTS is your peak value of nominal stresses, which is also denoted as sigma M or sigma U. Okay, during the test. Okay, and it is given as sigma M equal to F max, that is maximum force applied at this point divided by original cross sectional area. So this will be sigma M equal to F max divided by original cross sectional area. Okay, so from this stress strain diagram, we can understand that for plastic deformation or during metal forming processes, the stress domain which is chosen, it is between Y and M. Okay, point F we already understood. It is known as the final instability point or failure point. Okay, the material is break into two parts. Okay, so this is how we this strain through this stress strain curve, we can understand that which area will be useful for us during metal forming processes. Okay, so uh, from this tensile test, there are a number of properties that may be calculated. Another property is your ductility. You might remember that ductility is the most commonly defined as the ability of a metal to plastically deform easily upon the application of a tensile force. Okay, without breaking or fracturing. Okay, so from here you can see ductility is the most ductility is the ability of a metal to deform plastically easily upon the application of tensile force without breaking. Okay, so without breaking means we will not go beyond ultimate tensile strength. Okay, it is F max, which is corresponding to point M. Okay, so this is how we have we will try to understand ductility. So ductility is considered between Y and M. Okay, so how it is defined? It is defined in two terms. One is in terms of elongation. Elongation means how much workpiece can be elongated or can be enlarged. Okay, and another is in terms of reduction in cross-sectional area. Both of these terms are taken in percentage, that is in terms of percentage elongation or in terms of percentage reduction in cross-sectional area. Okay, in terms of elongation, how we can define delta equal to your change in length upon original length, or we can say change in length LF minus LO upon change in length will be LF minus LO divided by original length. So this will give you elongation. If we multiply it by 100, then it will give you it will give you percentage change in length. Okay, so it is given in terms of percentage elongation. It should be multiplied by 100. Otherwise, it is giving only elongation. Okay, and for calculating the same percentage in reduction in cross-sectional area, what we have to do? We have to do a original cross-sectional area, change in area. How we will identify original area divided subtracted by final area. Okay, so AO minus AF divided by original cross-sectional area. What it is giving? It is giving reduction in your uh, cross-sectional area. If you multiply it by 100, it will give you in percentage. Okay, so this is how we identify ductility. So from today's discussion, we can understand what are the desirable properties during the metal forming processes. So what are the desirable properties? Your yield strength should be low. Okay, if you see your stress strength curve, this yield strength should be low. There are a number of things through which this yield strength can be modified that we will discuss. Okay, but what is desirable during metal forming processes? This yield strength point should be low. Another desirable property is high ductility. Okay, the material should have high ductility. Ductility means that it should be easily enlargeable or elongable. Okay, because ductility is defined in terms of elongation or in terms of reduction in cross-sectional area. So the reduction in area should be easier, or the elongation should be easier. Okay, so this is how the desirable properties we can understand that in metal forming processes, low yield strength is desired, high ductility is desired. These properties are sometimes affected by temperature. Okay, so since your time is running, I will up in only in 1 or 2 minutes. Let me conclude it. So these properties are affected by temperature. Ductility, your ductility is high ductility requirement. It increases with temperature, as well as your yield strength, that is your yield point is decreased when we increase your temperature. Okay, so during metal forming, instead of working at room temperature, we can slightly increase increase the temperature of your metal block. Then it will be easier to deform the metal forming deforming the metal using metal forming processes. Okay, there are other factors. These are strain rate and frictions that we will discuss in uh, coming lectures. Okay, uh, from for today I will stop here. Okay, let me download the attendance so that nobody is remaining once. Okay. If there are any questions, you can write under the chat box. Okay. If there are any questions, you can write under chat box so that I can take up questions. Okay, I will wait for 1 minute more. If there are any questions, you can type under chat box. Here, I am stopping your recording, and I will send a copy of your